Here we have Johannes, Schipp von Branitz, who will tell us about primitive recursive dependent type theory.
Yes, thank you. Thanks for having me, and it's good to see you all. This is joint work with my PhD advisor, Ulrich Buchholz. He's also in the audience. And we have a paper about this. It's on the archive. You can find the slides on my website, jsvb.xyz. And, well, if you remember only one thing from this talk, then let it be this. If we have Martin-Leuven type theory, intensional or extensional, with natural numbers but without pi types, then everything you can construct is primitive recursive. And in fact, the theorem is a bit better than that. So I will make this more precise. But let's motivate this first and recall some notions. What is a primitive recursive function? Well, we have basic functions, constant function, successor, projection, and compositions thereof. And then we have a primitive recursion operator, which is essentially a bounded for loop. So we have some initial value g and some step function h, and we can construct new functions from that by applying h a couple of times to g. And this is a bit simplified because we can also have a tuple of natural numbers in the context, right? So that's one way to define primitive recursive arithmetic. And why do we care about primitive recursive arithmetic? Well, it's occurred many times as a basic notion of computability in formal meta theory and reverse mathematics. Just as an example, in reverse mathematics, you encode some theorem in a weak-based system, in this case, primitive recursive arithmetic, and then you have some more expressive system, and you check which axioms you need for your more expressive system to prove the theorem, which is encoded in the weak system. And encoding is the key word here, because if you have a weak-based system, then you need to do lots of encodings. And the more expressive your base system is, the less you have to encode. And if your syntax is closer to a proof assistant, you might also be able to verify your work formally. Now, what gets us beyond primitive recursion? Well, the Ackermann function is well known. One way to do this, so it takes two natural numbers as arguments, and I sort of presented this uncurried version here to make it clear that to define the Ackermann function, you can't just separately use the recursor on each argument, but instead you have to eliminate into a family. You have to eliminate into a family of function types. And the question is, if we don't allow elimination into function types in dependent type theory, does that ensure that we remain primitive recursive? And the good answer is, yes, that is indeed the case. So let's make this precise. We take MLTT, choose some syntax for it, or maybe abstract syntax. We chose higher order abstract syntax. And we restrict it to some bottom universe. We have a normal hierarchy of universes, but we don't assume that our bottom universe is closed under pi types, but we still have closure under sigma types and identity types. We have finite types and a type of natural numbers. And we also restrict the elimination principle of our natural numbers n to U0 small type families. And of course, because we don't have pi types, we have to state this in the open form. So if we have some U0 small type family, some initial value, and some step function, then we get a section of this U0 small type family X. And then if you take a pi type in our calculus, this takes you to the U1 universe. And then you can assume also that all of your higher universes are closed under pi types, as long as the universe in which you allow elimination into from the natural numbers don't have pi types. And then the adequacy result is that all definable terms, all open terms between natural numbers are exactly primitive recursive. And this is meant as a statement about the standard model in sets. So if you interpret this type theory, we don't have univalence or anything in the category of sets, then all functions between the natural numbers interpreting the syntactic natural numbers as actual natural numbers will be primitive recursive. So that's very nice. It's much easier to encode things in this calculus. What could make it even better? Well, we could consider adding the standard natural numbers with a large elimination principle, and well, we conjecture that this is true. These would need to be syntactically different, and then we could eliminate from those into any type family and get a coercion from primitive recursive functions to actual functions between natural numbers. We also think that it's possible to add finite inductive types such as lists, finitary induction recursion, and similar things. One interesting thing is internally in our calculus, we can already define a primitive recursive Gödel encoding of the codes in the smallest universe. And we think it's also true that we can have a judgmental variant of that. We haven't quite figured out the soundness proof for that yet, but that would be very nice because then we would actually have a universe within our universe, a universe containing itself. And that's not a problem because we don't have pi types. Then in the past, Hoffman, for example, in his work about polynomial computability, polytime type theory, used comonadic modalities to regulate the recursion operators, and maybe it's possible to add something like that here too to make recursion, simultaneous recursion possible. And then the question, well, the most interesting question is, how does this apply to homotopy type theory? Well, univalence as an axiom is not computable, so we couldn't assume that our bottom universe is univalent. But if we take something like cubical type theory, then it's quite likely that the same adequacy result is true. I mean, here we don't necessarily assume extensionality for identity types, but it's not quite clear how to adapt our proof for the adequacy of this calculus to the higher setting. We have some ideas, but it's not quite worked out yet. Okay, so now I'm gonna very briefly sketch. Oh yeah, just some more context. Due to Haberlin and Pate, we have the calculus of primitive recursive constructions. That's a sub-theory of the calculus of inductive constructions. And our work improves on that, and that we do allow pi types, and our syntax is more similar to something you have in ACTA. And then there's a lot of work of recursion in the context of type theory, and usually you use inductive domain predicates or other co-inductive types to talk about partiality. But of course, in primitive recursive functions, everything is total. Yeah. Okay. So how can you go about proving this? We use state commutability, logical relations, and a synthetic approach to that So the idea is we have our theory, T, and we present it as some structured category. And then if we want to prove something about T, we can define some functor rho, which sort of extracts information about our syntactic objects that we want to prove something about. And then if T is sufficiently nice and this functor rho is sufficiently nice, in this case, they both need to have finite limits or preserve them, then we can lift along the Yoneda embedding to the presheaf category. We call this lift rho hat. And if we take the comma category set over rho hat, also known as the Artin gluing, then that category is again a topos, so it has a rich internal language, dependent type theory, and T hat also embeds into this topos, and so does set. So we can use this internal language of this glue topos to construct logical relations over elements of the form rho of X. And what are the ingredients to the rho that we used? Well, for one, we want to make a statement about the standard interpretation in sets. So we do need to somehow involve our standard model in sets, and this interprets the natural numbers, the syntactic ones, as the actual natural numbers. But then we also need access to something which is always primitive recursive. And well, one could imagine maybe a syntactic approach where internally in the language we say we have some relation to something that's syntactically primitive recursive, but we chose a more semantic approach because it seemed more modular to us. So we defined another model in a Grothendieck topos R. And this Grothendieck topos has the property that the interpretation of our syntactic natural numbers, this is a natural numbers algebra which is not initial, that all of the endomorphisms of this object are primitive recursive, so we get direct access to that. And yeah, this is not a pre-sheaf topos, it's some sheafification of a certain category. And then we can combine all of this data by defining the functor rho, which takes some type x to the product of the global section, so morphisms out of the terminal object of the interpretation of x in this Grothendieck topos R, and then take the product of that with the model in set. And then, yeah. And then we glue along the lift of that functor. And one more ingredient we need, which we also need to prove separately, is that our calculus satisfies canonicity. So the closed terms of natural numbers are actually natural numbers. So if we have all of this set up, then any open term of the natural numbers can be interpreted in this glue topos set over rho hat as well, such a commutative square. So on the left, the natural numbers are interpreted as this family of global sections over rho of the natural numbers, or rho hat, doesn't make a difference. On the right side as well. And then because we have canonicity on the top left, our global sections of the natural numbers are actually natural numbers. And we can also show separately that that the interpretation, or that rho of the natural numbers is actually isomorphic to the product of natural numbers. And then because the square commutes, we see that the interpretation of f in set factors through the global sections of f, precomposed and postcomposed with the isomorphism to the actual natural numbers. And that also factors through through the global sections of the interpretation of f in this Grothendieck topos R, which is by construction primitive recursive. So that means that f in set has to be primitive recursive. Yeah, that's all I had to say about that. Thanks for your attention.
Okay, thank you. And do we have any questions?
Sorry, I missed something. So what is happening in this diagram here?
Okay, so
So what is delta in particular?
yeah, so we take the comma category along this rho hat, and this rho is given as this functor. Then we lift this and take the comma category along that. And an object of the comma category consists of some type x, a set S, and a function from S to rho hat of x.
Yeah, okay.
And in this case, our set S is the global sections of n, and well, x is n. And then because then we always sort of have this delta, which is sort of a diagonal, so we can interpret interpret such a global section in R and take the global sections again, and we can interpret a global section of n in set, and rho is exactly those two components combined. And then I squished this all together by saying, okay, actually, in this case, gamma of n are the natural numbers, and rho of n is a product of natural numbers. That's just a separate isomorphism.
So the maps on the left and the right here are the natural numbers objects in the glued topos then, or?
No, these are natural numbers as in sets. The natural numbers object in the glued topos is just the isomorphism, I think, the identity of the natural numbers over the natural numbers.
Okay. Okay, maybe. Okay, I'll ask you again. Yeah. Okay.
Anybody else? Yes. Now you're waking up.
You mentioned that an alternative to the logical relation that you did for your theory would be also to internalize the fact that you capture primitive recursive functions.
Yes.
And how would you go about doing that? Wouldn't that be like much more difficult to do?
Yes, probably. I mean, difficult enough that I didn't choose to go this way, or at least didn't go through the details. I mean, defining this interpretation in this topos R and coming up with this topos R and showing that this interpretation is sound also isn't exactly easy. That's like most of the paper is concerned with showing that this interpretation actually works. So I'm not sure which is easier. But the question is, how do you make the notion of primitive recursiveness available in your glue topos? So in your glue topos, you can define syntax for primitive recursive things and maybe relate to that. And here we sort of make it available by externally saying this is primitive recursiveness, and then from our external perspective, we know that the objects in the internal language of the glue topos actually refer to some primitive recursive predicates.
Thanks.
So you mentioned that there is a new elimination principle for term in NAT. If we assume that every term is constructed with constructible recursive function, so what is this elimination principle? You eliminate and definition. Okay, so yes, what is the elimination principle?
Okay, by that I mean exactly this rule, or at least that's one way to phrase it. So if we have some types which are all in the bottom universe, and then we have some g over 0, and then for each natural number and each x, we get some h in the next type. Then we get a section of this type family. So this is, I guess, non-standard because usually you don't assume that x is in U naught, but x is just some type.
Okay, but maybe there is not exactly one way to construct a function by using primitive recursion. I don't know. So.
Sorry, I did not understand the question.
Do you have the you don't have a unique way to construct recursively a function? So can you? I mean, can you do induction? Can you do dependent induction, for example, using this principle?
I'm sorry, I'm not sure what you're asking, but we can talk about this later. I mean, if your question is about uniqueness, of course, there's more than one way to define a certain primitive recursive function or to encode it. And we do have sort of eta and beta rules also for this rule. But this is just one sketch of the syntax because in our presentation we defined higher order abstract syntax, so we don't make a choice for variable rules. That's all taken care of by the logical framework. Yeah.
I was just thinking, it's maybe not so nice just to have natural numbers. You would like, it seems from the type theoretic point of view, it would be natural to have all algebraic data types. So it seems to me that you could have a special version of the W type, and also exploit the fact that there's a universe of finite types, and the pi types with finite types exist in your universe, and this way one could capture all algebraic data types instead of just having natural numbers.
Yeah, that's sort of what I was trying to hint at in the second point here.
Yeah, okay.
The thing is, for every construction you add, you have to, of course, make sure that your model in R and your model in the glue topos also is still sound.
Sure.
So that is some work. But yes, I think that's possible.
Yeah, gotta stay sharp. All right, let's thank Johannes again.